Hello everyone, I'm Qifan Yu from Tsinghua University, and I'm honored to introduce our work in MOOC, ExpanRL, which is a hierarchical reinforcement learning framework designed for course concept expansion in MOOCs. In this talk, I will introduce our work in four main sections, including the introduction of our task, some necessary basic settings of the site expansion, while presenting the interactive MOOC environment, as well as our proposed method and some necessary experimental results of our task. First, I will introduce why we need to do the course concept expansion task in our science. In education domain, there is a saying that educators should support students' autonomous learning by providing extra knowledge of a course. In the MOOC environment, there are many related and useful concepts, but they are out of teaching. For example, when a student learn LSTM concepts in a MOOC course, some very useful concepts like RN, transformer, and machine translation task are also very useful for his learning. However, these concepts are not valuable if the student never sees them in the teacher's seeing. Without specific mention, these concepts are never available for them. Thus, we need to find more extra concepts for students for better learning. But when we want to do this, there are a few challenges in MOOC to prevent us to the final target. For example, as the concept like RN is a related prerequisite concept of the LSTM, but the machine translation is a useful task for the concept. There are different reasons for a concept to be related to the course, so if we only use contextual information, it's not enough in this task. Second, courses are often combinations of multiple categories, which is easy to cause semantic drift. How to limit the semantic drift during expanding is a very typical challenge in the set expansion task, and in MOOC science, it is more severe. And MOOCs are updated continuously. Numerous new courses arise every day. How to ensure the generalization ability of the expansion model is also very need to be concerned, because if for each course we need to train a new model, there will cost a lot. Our solution, as well as our contributions, are presented here. First, we apply a hierarchical reinforcement learning to our best knowledge is the first attempt in expansion task. Then, we design a framework which separately models the seed selection task and the expansion task. Third, we build a dataset from real interactive application in MOOCs and provide some results for the researchers in related domain. Before we introduce our model, we need to first present some preliminaries of our task. The first is about the task of site expansion. The general site expansion task refers to the practical problem of expanding a small site of seed entities into a more complete site by discovering other entities that also belong to the same concept site. For example, we provide 3 seed concepts of countries. Our aim is to build a large site including them and find more similar concepts like Russia, Canada, Japan, Brazil, and so on. The problem can be defined as this. Our input is a small set of seed entities, and we can get the candidates from an external resource. And the output of our task is the expansion result, which is a larger set of the seed set. For evaluation, we usually use mean average precision to evaluate the ranked score result list. And there is another background, is the MOOC environment. There is a recent idea of collecting user annotation from real science that by building an interactive game like below. In this instance is a real example from the course Introduction to Biology. We built a very interesting game that a student can delete some unrelated concepts during the learning. That is, he will get some bonus depends on the delete result, but the delete action will be recorded as the noisy annotations of our task. Given the interactive environment like this, and how we can build a more novel model to the set expansion task in MOOC is our concern. Our method is presented like this. The framework is very clear. It includes a high-level RL, seed selection stage, and a low-level RL expansion. The whole framework can be run like this. The high-level RL, given a course concept set, we can select some useful and important seeds into the low level, and the low level RL will take this as an input and scan the whole list of the funding candidates and finally get expanded ones. This process will iterate until the site is large enough or there is no high quality candidates to be expanded. The high level RL is the seed selection stage. The option of this agent is to select the seeds. The state is the given site, and the reward can be only refreshed by the low level RLs ended. And the policy we use is to optimize the seed selection stage. For the low level RL, we change the action to judge whether a certain candidate should be expanded. The state is given from the candidate list, the seed site encoding, and a zero vector. The reward is given from the interactive game. That is, if the selected one is deleted by most of the students, this reward will be turned to be negative. But oppositely, it will be positive to give the model a good reward to find more helpful concepts for students. And the policy is also optimized like this. Here, we come into our experiment because our framework is not so complex, but the experiments can confirm that our presented HRL framework is worked. The dataset, which is one of our main contributions, is built from 6 subjects, which including 3 interdisciplinary datasets, and we have annotated over 6,000 extracted course concepts and collected about 500,000 user behaviors from real interactive MOOC environment. The subjects are math, chemical, biology, material science, architecture, and computer science. And the interdisciplinary dataset is more hard to collect, but we also built from over 13 courses. The baselines are the typical baselines from the set expansion task, as well as a pipeline method from our previous work. The evaluation metric is introduced as before, and the overall experiment can be found there. Our model performs better than all of the other baselines in the 9 datasets. What's more, the CRL and PRL are two different kinds of RL method, which replace the seed selection high-level RL with two rule-based method. It can be seen there. The RL method can perform better in the complex MOOC environment, and our hierarchical RL method can perform better than the rule-based high-level RL. That means the seed selection stage, which is ignored more in previous works, is also potential to be a good optimization stage. For the generalization ability, and our method build a good performance in this experiment. We only give the model 5 or subjects into the training, but use an extra one as the test site. In this setting, our method still performs well, but most of the supervised methods declined severely. And for different seed sites, we find our method can perform stable. That means this method can perform not so changeable in the applicable science. For the other way of the evaluation, we also built an online evaluation in real science, and the lower click rate means the better result. In this setting, the hierarchical RL method can perform even better. Truth be told, I think ExpanRL is a very a not so trivial attempt, but provides some interesting ideas for us. And we have many more complex MOOC applications in our real tasks. We are the THU MOOC team, and we present a very interesting data set, MOOC data. If you are interested to the MOOC application or education applications with NLP research, you can contact us from this website. And there are many our data set and interesting work introduction. And we also built an interesting agent Xiaomu in the real MOOC science, which can support the QA and knowledge recommendation and so on. If you are interested, please contact us for this. Thank you very much.